back to our channel, and this time we are going to understand how to make a cascading of multiplexers, in which we learn how we can make large size multiplexer using a smaller size multiplexers. So as you can see on your screen, here is the diagram of a 4:1 multiplexer that we want to make up. And for that, we are using 2:1 MUX. So this is the first one, this is the second one, and this is the third one. So we know that for the 2:1 MUX, you have got two input lines, I0 and I1, and one output line. For another 2:1 MUX, you have got two input lines again and one output line, which is small letter y. And it has got a common and a single select line that is called as S0. Okay. So here is the select line. So as you can see that 2:1 MUX is like that only, where you have two input line, single output line, and only one select line here as well. And S0 indicates that it is a select line that is common to both of these MUX. Now, the output of these two individual marks, which are X and Y, they become input lines to the third and the final 2:1 marks. And it has got a single output line that is indicated by letter Z. And obviously, since it is also a 2:1 marks, you have got a single select line letter indicated by S1. So S1 is the most significant bit and S0 is least significant bit. This will get to know when we'll have the truth table of this complete 4:1 marks, and we'll understand how this multiplexer will perform as a 4:1 marks. So we'll see that in the form of truth table. Remember, the job of the 4:1 marks as a composite, it will have four data input lines and single output line. So which is what precisely we see here. So you've got 2 plus 2, four input data lines. If you see in this dotted box, outside the dotted box, right here, you've got four input data lines and only single output data line. And essentially, with these two combined, S1 being MSB and S0 being LSB, you've got two select lines. That is what essentially makes your 4:1 MUX, which is, you can see here, the definition of the multiplexer is 2 to the power n is to 1 MUX, where small n indicates your select lines, not an input line. This is the select lines. One is the output line, and 2 raised to the power n becomes your input lines. Okay, I repeat again. 2 raised to power n is to 1 MUX. That's the standard definition, where small letter n indicates select lines, 1 indicates the output line, and the 2 raised to the power n indicates number of input data lines. So note the difference between input data line and the input select lines. So if it is a 4:1 marks, that means n is equal to 2. Therefore, 2 to the power 2 would become 4. That is input line, and 1 obviously is your output line. Now let us head to the truth table of this to understand how this works. So here you see that you got the truth table of this multiplexer that we can understand. S1 you have MSB and S0 you have LSB. That they are your two select lines, and single output line is output Z. That is the definition of 4:1 MUX. So you now can see that there are obviously four possible combination, because there are two select lines, 0, 0, 0, 1, 1, 0, and 1, 1. So let us have understanding when S0 is equal to 0. So there are two cases right here when indicated by the shaded graphs here. So when S naught is 0 right here, I naught from the first MUX and I2 from the second MUX should be available at X and Y respectively. Now, whether the X gets transferred to Z or Y gets transferred to Z, that depends on whether S1 is 0 or 1. So first case, when S naught is 0, as I said, I naught and I2 should reach to the output Z, and that depends on whether S1 is 0 or 1. So when S1 is 0, S1 is 0 here, the whatever is available from the input side to the X gets transferred to the Z. That's what I naught comes here. When S1 is 1 in the truth table and S0 is still 0, so obviously I2 through the Y gets connected to the Z. Next case, without a shaded graphs, this row and this row, S0 is 1. S0 is 1, it means I1 and I3 are available at X and Y respectively. And whether X or Y gets connected to the Z depends on what is the value of S1 here. So in these two rows, if S1 is 0, X gets available to the Z and X has value of I1. That's why we see I1 comes here. And when X S1 is 1, you have Y gets connected to the Z and essentially I3 gets connected to the Z through the Y. And that is how you see that this is the condition. So this is how the complete 4:1 MUX has been realized using three smaller 2:1 MUX in the one box. So hope you understood the definition and this block diagram. Now, the next case, let us say assignment is to create 8:1 MUX right over here. And 8:1 MUX can be realized by using 4:1 MUX in the quantity of 2 and one single 2:1 MUX. So definition of the 4:1 MUX is that you obviously have four input data lines, I0 to I3, and four another data input lines from I4 to I7. And each of these 4:1 MUX have two select lines with S0 and S1. And then you have single 2:1 MUX. Obviously, it has got two data input lines, let's say X and Y, and it has got single input select lines in the form of S2. And finally, you have output of this. So in the dotted box, you've got this internal structure, but outside you've got a definition of 8:1 MUX where you see from I0 to I7, you've got 8 input data lines and single output line. And obviously, again, if we look at this definition, N is the number of select lines. There has to be three select lines, S2, S1, S0. So S2 being the most significant bit and S0 being the least significant bit. So obviously, three input select lines, one output line, and 2 to the power 3 because n equal to 3 becomes 8. That is how you have got a definition of 8:1 MUX. So now how this discrete blocks when put up in a single box will become a major or system level 8:1 MUX that can be understood with the form of truth table. So here is available a truth table of this multiplexer that we can see that. So obviously you see that S1 and S0 in this form of the first shaded one, they have four possible combinations 0, 0, 0, 1, 1, 0, 1, 1. S1, S0 are here. So in this two, S1 is most significant bit and S0 is least significant bit. Now, when S1, S0 are 0, 0, 0, 1, 1, 0, or 1 1, the job of the multiplexer is that these four data input lines are available here at the X. Similarly, uh, and in that case, S2 has to be equal to 0. So when S2 is 0, your X gets connected to the output Z. That is what you see in the first four rows right over here. They have four possible combination S1, S0, and S2 is 0. However, for another four set of rows where S1, S0 takes the four possible combination and S2 is 1 now, obviously I4, I5, I6, and I7 through the output Y gets transferred to the Z. Depends on what possible combination of S1 and S0 you select. So this is how we got to know how 8:1 MUX can be constructed or made using 2 4:1 MUX and 1 2:1 MUX. Now, this is the final form of the making of 8:1 MUX. So you can see that 8:1 MUX can also be realized using 4 2:1 MUX, as you can see, and one single 4:1 MUX. So again, since it is 8:1 MUX, you got four input data lines ranging from I0 to I7, three input select lines from S2 to S0, where S2 represents the most significant bit and S0 represents the least significant bit, and 4:1 MUX, where the final data line, output data line is Z. So right here, you can see the truth table of the 8:1 MUX. So what you see here for the 8:1 MUX is you've got the four input data lines, that is I0 to I7. You've got the single output data line, that is what, and three select lines ranging from S2, S1, and S0. So truth table is very simple, where you have first, let's say, S0 that can have 0 or 1. So when it is 0 indicated by the greens, the output Z here, actually it is a Z, should get I0, I2, I4, and I6. So you see that I0, I2, I4, and I6, they are available at these output lines. Okay. And now they get available when you have S2, S1 to be 0, 0, 0, 1, 1, 0, and 1, 1. These two select lines should be like that. However, when S0 is equal to 1, which is indicated by the gray lines, S0 is 1 here, then your I1, I3, I5, I7 are available at these lines, which are the input data lines to the 4:1 MUX. And which of these output lines gets connected to the final output line depends on if your S2 and S1, the value of them should be 0, 0, uh, 0, 1, 1, 1, 0, and 1, 1. So this is how you can see that your final output gets reached to the all the input line depends on all these possible combination. So hope you found this model useful about cascading of multiplexers. If you did so, share it with others for wider reach. Stay tuned for more engaging content like this, and till then, wish you happy learning.